We continue a series of talks devoted to our recently submitted papers to iClear, and today's speaker is Andrei Atanov, who'll give a talk about resistant research on deep weight priors, authored with Arsenia Shucha, Kirill Struminsky, myself, and Max Welling from University of Amsterdam. And as previous speakers, this talk will be about the application of implicit probabilistic models to the problem of Bayesian inference in extremely complicated high-dimensional spaces. So by implicit probabilistic model, I mean neural network that is capable to generate samples, that is capable to approximate very complicated high-dimensional distribution, but approximated in implicit manner rather than explicit. So we cannot have access to the value of density function, but we may very efficiently generate samples from this distribution. And I think that this direction is quite promising, and it will provide us new tools for probabilistic inference in the complicated models. So one of the tools will be presented today.
Hello everyone, thank you for the introduction. So today I'm going to tell you about our joint work, deep weight prior, with Arsenia Shucha, Kirill Struminsky, Dmitry and Max Welling. So let's start. Today during my talk I will consider the simple setup of Bayesian inference for supervised machine learning problem. So we have a data set of object labeled pairs, likelihood function, which is distribution over y given x, which is parameterized by the vector v. So, and the last but not least, the prior distribution over these parameters v. So, and then we transform our prior distribution using Bayes rule into posterior distribution over parameters v. So, however, this fraction, the denominator of this fraction is the evidence, which involves integration over high-dimensional space. And in the case of deep neural network, we cannot calculate or somehow estimate it precise. So we use variational inference, where one of the components appear its variational posterior distribution Q over V, which is parameterized by theta. So, and the idea is to minimize the Cayley divergence between our variational posterior distribution Q and the true posterior distribution V given data. So, and since we cannot directly minimize this quantity, we maximize so-called evidence lower bound, which guarantees us the minimization of Cayley divergence. So it looks as follows. The first term is data term, which is expected log likelihood of our models sampled from variation posterior distribution. And the second term is kind of regularization, which is kind of divergence between our variational approximation and the prior distribution TOV. So, and it ensures that we don't go far away from our prior distribution. So, and during my talk, I will talk about prior distribution from this framework. So, with the prior distribution, you can incorporate your knowledge, your prior beliefs of parameters and some specific properties of your parameters into final model. So, and it has been shown that it's quite useful for quantization, classification, and so on. So, all these specific prior distribution for these properties are quite useful. They are usually fully factorized. Yeah. And thus they does not capture any intrinsic structure of your parameters. And actually it may be the case that your parameters have this particular structure. Yeah. For example, let's consider convolutional neural network. They are based on this operation of convolution, where you have the kernel, which is a matrix, weight matrix, and you place it in different position of your image and convol the value of pixels with your matrix kernel. So, and on the right side you can see the convolutional kernels learned on CIFAR10 dataset, and as you can see that they have this particular structure. They capture some patterns from your image, either lines or some blobs, corner, edges, and so on and so on. So, however, when we do not have large data set to learn these structured kernels, they may look as follows, as complete noise. Yeah, and these kernels will learn on a small subset from CIFAR10 dataset, and we have this drop in test accuracy. So these kernels generalize poor in comparison to these ones, and so still when we train our convolutional neural network on a small dataset, we still have this this prior knowledge, strong prior knowledge about the form of the structure of convolutional filters. Yeah, and we can incorporate this knowledge into our prior distribution to favor learned kernels.
Yeah. One question. In this experiment, you assume only some optimization issues, or if you start the training of your network from the good solution on the small data set, you still come to the noise?
No, I think if you start from good initialization, you end up with good filters.
So it's only an optimization issue here.
Yeah, it's like you're overfitting.
Okay.
Yeah.
I don't think it is an optimization issue because good test performance does not come from good optimization on the training data set.
But we're not speaking about test performance.
Yeah, it's about generalization.
Probably training error of both models will be zero on the training set. So the training objective will be zero. So it has converged to optimization, converges to global optimum.
Yeah, sure.
And then what about the test? Well, that's the question.
Yeah. The point is these kernels generalize poor. And we can incorporate this knowledge into our prior distribution. So we'll consider the following factorization of our prior distribution over layers, channels, and filters. So your convolutional part of your network consists of L layers, and each convolutional layer consists of several filters. Yeah. You can see on the right. And each filters consist of stacked kernels of the number of channels of your image, input image. Our prior will be shared over kernels of one layer, so we will factorize over all kernels, and it will be different for kernels of different layers. Yeah. How can we actually develop or construct such prior which will favor the good learned kernels? So the answer is generative models. We will actually learn our prior distribution, and let's examine it in more details. So let's imagine we want to perform a Bayesian inference on a small dataset D2. Yeah, for example, it's a dataset of RGB images. So we take a large dataset of RGB images too. We train a convolutional neural network on this large dataset D1, or maybe a few convolutional neural networks. Then we use these train networks, which are generalized well, and collect datasets of kernels for each layer from these learned, from these trained convolutional networks. Yeah. And then, using these datasets of learned kernels, we train our prior distribution using generative modeling framework. And then we use this learned distribution over kernels as a prior distribution for Bayesian inference on a dataset D2. Yep. Let's consider two families of distribution. The first one is explicit models, which directly models the distribution over parameters, over objects, V. So it can be kernel distribution, normalizing flow, or pixel and so on. The main advantage of these methods is that you may compute the probability density function at any point you want. And you needed to estimate cat divergence term in evidence lower bound. Yeah. However, all these models are cumbersome and slow, and it makes your steps of variational inference have high cost. Yeah. So another family is implicit distributions. Now we will consider implicit distribution in the following form: the mixture of explicit conditional distribution V given Z and explicit prior distribution over latent variable Z. And this conditional distribution will be modeled as a neural network for expressiveness. And from that, we cannot calculate this integral. And so we have no access to probability density function. And therefore we cannot estimate, we cannot calculate the cat divergence, and we cannot construct an unbiased estimation, since we cannot calculate at any point the probability density function. So, however, these models are more efficient in terms of memory and computational costs. So, and we will use variational autoencoder framework to train these conditional distribution. So, here it is. For each convolutional layer, we train our prior distribution as follows. We train variational autoencoder on the collected learned kernels of these trained neural networks. Yeah. We train encoder and decoder as usual in variational autoencoder, and then we use the decoder, the reconstruction part of variational autoencoder, and define our prior distribution as follows in an implicit form as the marginal distribution over V. It is the expectation of our reconstruction model over prior distribution of latent variable Z. Yeah.
So two questions. First is how many training samples do you have for this variational encoder?
For training this variation, yeah,
yes.
A lot. You have 100,000 kernels.
So you have single variational encoder for all the weights you have?
For all different, we have one variational encoder for all kernels of one convolutional layer. Yeah. We have different autoencoders for different layers.
But it's on average like 500
We train a lot of neural networks.
Okay.
How many?
I
mean, different architectures or
no, the same architectures from different initialization.
But it seems too much, because you need, I know, hundreds, at least hundreds of networks.
Maybe at
I
most, 100 at most. We train.
I think that maybe our audience didn't get that we define kernel as a square of h times v, not like three-dimensional tensor. Our kernels is
our kernels is like
two-dimensional.
this single rectangle from here.
So it's two-dimensional.
Yeah. It's not a whole filter. It's one kernel.
Yeah.
Is it true that this assumption that all kernels can be generated by the same network assumes some factorization properties of the kernel tensor?
Can you repeat it again?
Is it true that you're basically trying to find low rank factorization of a high rank tensor of your kernels
Yeah.
by sharing by using single network to generate them all?
Yeah, sure. It's like
So
it's how variational thinker works.
So you don't assume a dependency of the weights on one layer at this storage, right?
So we consider we assume that kernels are independent.
Yes, here you assume, but when you take the integral, it will generate all the kernels for the kind of...
No, we generate like single kernels, which is it's rectangular, one-dimensional, like two-dimensional.
Okay.
So here we consider like the weights of our kernel V, or one kernel V, are independent given Z. It's like it's how variational tensor works. Okay, we like this variational distribution doesn't assume that our weights in one kernel independent, but here,
But different kernels are independent.
yeah.
Right.
Is it a reasonable assumption that
Well, it's
It's much more reasonable than currently used assumptions of full
Yes.
factorizability.
One can you can like actually model the distribution over all filters. It will be more reasonable, but it's much harder. You know.
So now the most interesting question is that we have a variational autoencoder which is able to generate new kernels if trained properly, but we cannot get access to the exact value of a probability density function in the space of kernels. We can only generate from them. And for training this variational autoencoder, we need to establish some kind of variational R bound, which requires us to have access to the exact values of a probability density function, which we do not know how to compute.
Yeah.
And this is actually the topic of this talk.
Yeah, let's consider it in more details. So, as I have mentioned, as George mentioned, so to compute the evidence law bound, we need to estimate the data term, which doesn't depend on the prior, so we have no problems here. So, and the second term is scale divergence. And actually it depends on the prior distribution in principal way. So let's examine it. Here we have, these scale divergence, the whole scale divergence over all of the variational distribution over all neural network and our prior distribution splits off into the sum of scale divergence of our single kernels because of this factorization over kernels we have for prior distribution and for variational approximation. So let's consider this amount, the scale divergence for one kernel of our variational approximation and the prior distribution. It looks as follows. The first term is the entropy of our variational approximation, which we either can compute analytically or use Monte Carlo estimation. So, and the second term is the expected log probability of our prior distribution. And our prior distribution itself is an expectation. And since this expectation is inside the logarithm, we cannot estimate it unbiasedly. Yeah, when we like sample z and then we given z, we end up with unbiased estimation of this expectation, but not the logarithm of this expectation. Yeah, and we propose to construct the upper bound on these scale divergence. Yeah, and so let's consider how to do this. So the first row is just the definition of scale divergence. Yeah. Then we take an expectation of logarithm of prior probability. It doesn't change anything because like your prior distribution does not depend on z. And this R actually is the auxiliary inference distribution. So then we re-express the marginal distribution, the prior distribution, which is the marginal distribution over V, and the joint distribution over V and Z, divided by the true posterior distribution of V given V. Yeah. And also we multiply by 1. Yeah.
Is it the same as in elbow?
Yeah,
Yes.
actually we use the same technique and the elbow for variation of the encoder. Yeah. So then we rearrange these terms under the logarithm, and we end up with this expression, which consists of two terms. The last term is the expected scalar divergence, which always is non-negative, and that the minus this expected scalar divergence is always non-positive. Yeah, and therefore this first term in the green box is the upper bound for the scalar divergence. Yeah, and this upper bound is the tighter, the better our auxiliary inference distribution R approximates the true posterior distribution V given V. So, yeah.
So R here is the same thing that it plays the same role as encoder in previous.
Yeah. You can use actually this encoder from VAA we already trained, and also we will see how can train this R during variational inference.
But also you can optimize variational bound if you already.
Yeah, with respect to parameters of this parameters of auxiliary inference.
And is it true that both this subjective and objective that you use when training the initial autoencoder are optimizing the same thing for the encoder distribution?
Yeah and no, because here your weights, your objects V comes from distribution Q, and for variational autoencoder, your weights V comes from another distribution. Yeah. So here you have expectation of this divergence between R and prior distribution. Yeah.
Does it mean it's better to use different encoders to model the posterior of Z given W? Or we may use the same encoder?
We use the same encoder in our experiment.
Did you try to use another?
We try to optimize the parameter during variational inference. We try to initialize it with encoder from VA, and then fine tune it. So, did I answer your questions? Then using these upper bounds for 1 month. So the whole term splits off into some over all kernels, over layers, channels, and filters in each layer. So, and for each scalar divergence, we use this upper bound. It's just copied from here. Okay. So, and then we can construct our final auxiliary lower bound on lower bound. And it looks as follows. It's just data term minus our L bound. And now our auxiliary lower bound depends on two sets of parameters, theta and psi. And optimization with respect to psi gives us a better, the tighter. You make this lower bound tighter between auxiliary lower bound and the elbow. And optimization with respect to parameter theta, actually optimize the lower bound. And note that in contrast to empirical bias procedure, the parameters phi of our prior distribution. So our prior distribution, you can see here, depends on parameterized with parameter phi L for each layer. So, and we fix it during the training.
But when we can continue updating the parameters of encoder.
Yeah, psi is parameters of encoder.
So first we adjust psi on the independent data set, which contains of different kernels, right? And then we continue updating it during the inference procedure.
Yeah, with respect to this objective function. Let's examine the final algorithm step by step. So we need data set. This the algorithm of stochastic variational inference with deep weight prior. Yeah. So we need the data set of objects and labels. Then we require the form of our variational approximation Q over the weights, which should allow reprioritization for optimization purpose. And the form of reverse models R. Also we require the prior distribution, which consists of reconstruction models with parameters phi and priors of these auxiliary variables D. So on each iteration we first sample the mini batch of objects from our data set. We sample weights from our variational approximation with reprioritization. Then, given these samples of weights, we sample the auxiliary random variables from variational approximation R over latent space. And then we estimate the auxiliary lower bound as follows. First is just data term, expected log likelihood of our mini batch. Then here you can see the lower bound on K term. So the first term in algorithm is one sample estimation of this entropy of our variational approximation over the weights. One can actually use the analytical expression if we have so. Yeah. So the second and third terms are one sample estimation of these divergence between auxiliary variational approximation R and distribution over later variables, prior distribution over later variables, which can also be calculated. Given V, it can be calculated analytically in some cases when you have this Gaussian distribution over Z. And the last term is just estimation, one sample estimation of the last guy. Let's move on to experiments.
And also you have another step for updating phi.
No, we keep
The
phi
is fixed.
fixed because it's parameters of our price.
It's not empirical bias.
It is not written here, so there is a big block in the beginning.
For training the...
Yes, all this.
Yeah, we are taking a gradient of these.
Well, that's an algorithm for stochastic variational inference with already defined implicit prior distribution.
Yeah,
So we first trained prior distribution, or adjusted prior distribution on our previously observed data. And now, how it works when we are using this implicit prior distribution for our variational inference for a particular given problem, which is assumed to be quite small data set. Because in this case, we really need a prior over convolutional kernels.
Yeah, we only take the gradients with respect to theta and psi, and update them.
I have one question. If you update, so assume that you have trained deep weight prior, right? You have implicit prior distribution. So you have adjusted both phi and psi, right? Now assume that you have, say, several small-scale data sets, and you would like to use this implicit prior distribution over the weights of convolutional kernels. So when you perform stochastic variational inference, you are adjusting what? Theta and psi. So assume that you've made it for one problem. Now the second problem comes in. So again, you need to adjust theta and you need to adjust psi. What initial approximation will you use for psi? The psi from the learned prior distribution or the psi from the first small scale problem? You see the point?
Yeah. So, actually, we, in our experience, we tried to optimize psi using this framework, but it doesn't like change anything actually. So because like this approximation of psi from variational autoencoder is good enough,
Okay.
and we like
So
can not optimize, and
So,
that's why we can use both of them, like, and it doesn't change anything. I think so.
okay, sounds reasonable, but still, you're still trying to optimize it. So probably it doesn't change much, but well, okay.
So in cases where you didn't get with your prior, so you okay, you can train your prior, and it can be actually like not good enough. And then your these samples from your variational approximation will be much different than once you trained your prior on. Yeah, here for your prior distribution you use the kernels learned on this external data set. And here you use and here for these scale divergence you use samples from your variational approximation for these stuff. And it can be much different.
Okay.
And then maybe you should like train psi because they are from the different domain. They come from different domain. And your like inference model didn't manage it.
Why don't just find the maximum posteriori rates? Why do variational inference?
So one can use it just for regularizing, yeah. But on a small data set, you will usually want to like train your ensemble. Maybe it will be better.
Have you compared map solutions with variational Bayes?
No, actually no.
Well, this was made mainly to make the scheme end-to-end. So we'd like to understand how the procedure of variational Bayesian inference changes if we start using implicit prior distributions. This was our main goal. And it appears that, well, it is actually doable.
So let's move on to experiments. So in our experiments we use like two setups. Yeah. For the first step we first train several convolutional neural networks on not NIST dataset, which looks as follows. It's just
it is an
10,
not NIST?
not NIST.
Okay.
It's data set of 10 letters of different fonts. Yeah. So we train a lot of convolutional neural networks on these data set. Then we like collect the kernels from these from these trained neural networks. On these kernels collected kernels, we train our prior distribution, and then we use this prior distribution for Bayesian inference on a small subset of NIST dataset. Yep. So, and for the second setup, we use the same, but we train our prior distribution on the network trained on FART 100 dataset, and use this prior distribution for the Bayesian inference on a small subset of the FART 10 dataset.
What's the fraction of this small?
We will see it here on plots. Here you can see the plot, the dependence of test accuracy on the number of examples we used for variational inference. Yeah, as training data. So blue curve is like for DVP, the orange one for log uniform, which actually corresponds to variational dropout. and the green one is for standard normal distribution. So, and you can see that for both setups, like DVP is marginally better. So, and from this you can note that when the number of examples increases, the gap between deep prior and the other priors like disappear. Yeah. This is because when you have enough training data, you can train these well generalized kernels, convolutional kernels by your own. Yep. You don't need this prior distribution to show you how they should look like. Yep.
And what about warm start? If you start training your network with standard normal distribution, but from weights trained on the big data set.
Yeah, but it's just like it's a good question.
I also really want to ask this because as a practitioner, this is a super important question.
Yeah.
Because you are actually doing transfer learning from big data set to small data set. So there are two standard approaches. One, just train on big and then initialize from that and continue. Another one, on top of that, just freeze most of the network and then fine tune the top.
You have here you have two like problems. First one, it will be just like initialization. It don't allows you to receive this like ensemble, variational ensemble. Yep.
Where is
And
variational
you still always.
Where is variational ensemble here? So here you report accuracy on this. So you can do that for non-Bayesian, like just standard technique. Standard
Yeah, but even on smaller sets, you want like more utilization.
Well, have you tried like direct transfer learning approaches?
No, we didn't try it
I don't,
because
you can do that. Exactly. But first of all, as you use this just for initialization during your optimization process, you have to tune a lot of hyperparameters just to.
The whole digital community has been doing this for many years, and they
let me
survive.
complete this. You can, when you use very small data set, you really have to jump to completely another point in your weight space
You freeze
What
most
about
of the network.
and overfeed this small data set.
What about
You freeze most of
be
the
it
network for that.
Yeah,
Like everything except
I
the
mean
last
that
layer.
you have to choose which layer
Everything
do you want
except the last
to
layer.
freeze and stuff like that. So this is the first reason. The second reason, you need to store the whole network. Actually, in our approach, you need to store several generated models that potentially may take much less kind of memory, disk space for the storage.
But
It
you
depends.
need a model for each layer.
Yeah, but they are pretty small because you generate filters in very small space, like 5 by 5 or 7 by 7. It's
So you're
very small,
Yep.
small
You're
space.
comparing the model to generate filters against just some number of filters already generated.
Yeah.
That's kind of a tricky comparison.
But actually, we can compare it in terms of number of parameters, and maybe it's okay. Yeah.
okay, and another reason is because, for example, this technique where you have prior over your kernels, you can apply it for like different architectures.
Another question is, have you compared this approach to approach based on explicit models like multiplicative normalizing false, where you can do explicit inference?
Yeah, they didn't get any advantages in terms of accuracy, but they like have much like they have high these computational costs and memory, but they didn't give us any advantages in terms of accuracy.
And advantages with respect to what?
With respect to like implicit models.
But you don't have any comparison on this kind of graphs.
Yeah, but we like tried it
And where do these computation complexities come from?
Because
Okay,
you
because if you use some kind of real MVP or other type of routes that is reversible, you need to save the width of your network, and you have to put a lot of layers. Every layer consists of several neural networks, so it's really bulky model, I would say. Very bulky model. Trust me, because I tried it.
Yeah.
It's super slow. And also, the third point about comparison, here we just put our goal as create new prior distribution for variational inference for convolutional neural networks. We do not put goal that want to beat every transfer learning methods, because of course this is very general method, and of course probably it will perform much worse than every very special method for fusion learning or something like that. Here, this work just about prior distribution for convolutional neural networks, not about transfer learning, really, not much.
Well, you can see just as a toy example on which we can compare different prior distributions, and that's it.
Yep. Here you can see the realization of the latent space. So we trained the deep weight prior duration of the encoder with the dimension of latent space equals to 2. And here you can see the embedded kernels into the space. And for the red dots, you can see the reconstructions. Yeah.
By the way, which architecture do you use for your variational encoders for all layers?
Like 5 layers, convolutional, variational of the encoder.
For all layers?
Yeah. With
you use the same architecture for all layers?
Yeah, but with a bit different hyperparameters. Maybe like this latent space dimension, but 5 layers. Yes. Always. Yeah. They are almost the same. Yeah. Okay, let's move on to another experiment, which is called random feature extraction. So your convolutional neural network consists actually of 2 parts. First one is convolutional, which you can think of as a feature extractor, and then you have fully connected layers, which gives this vector representation of your image given by convolutional part, and then it makes the prediction. And it has been shown that when you simply initialize the convolution part of your neural network with random weights, it's already gives you, and train only fully connected layers, it already gives you good performance, better than using just pixels as the features. Yeah. So in this experiment we keep this convolution part fixed and train only fully connected, and we compare different initialization. The random Xavier initialization, like random initialization of each weight, and the second was initialization of kernels as the samples from our deep weight prior. So in deep weight prior we can sample these latent variables, pass them through the decoder, and end up with a filter sample from our prior. Yeah.
So the fixed part of
Yeah. We initialize convolution part neural network with either randomly with Xavier or with DVP, and train only fully connected layers.
Oh, I see.
Yeah. And here you can see the dependence of test accuracy on the size of convolutional part of the model. Yep. And you can see that for both means and for setups, it performs better. And also, you can here we plotted the initialization from filters, which we used for training our deep weight prior. So for our deep weight prior, we use learned kernels to train on. So, and we try to initialize neural network, the convolution part of neural network, with these lower filters. Yeah.
In random order?
Hmm?
In random order?
Yeah,
or?
sure. Okay. Randomly. So, and you can see it performs better than decoder prior, but still, for decoder prior, you only need to store the decoder part of your variation of the encoder. And for filters, you need to store all these, a lot of filters, actually. Yeah.
So presumably the green line here indicates the maximum possible performance for the best generative model you could have trained on this data.
Yeah, we can think of it. Yes.
Okay.
When you showed samples from your DVP, it looks like that matrix just have some regularity structure. In terms of matrix, that we can conclude that it's just low rank matrices. And the question is, what will be if you will be generate random filters, but not arbitrarily random, for example, Xavier, that obviously Xavier is better initialization for convolutional filters, but just throw some low rank samples and then compare. And maybe we did not need such complex encoder-decoder to generate just some matrices with low rank structure.
Yeah, you mean for this random feature structure experiment, yeah? Because you need actually the distribution for these variational fields. Here you need like distribution over these filters.
Yes.
Yeah. And yeah, for this random feature extraction experiment, yeah, maybe it sounds interesting, but we didn't. Maybe it will work. Like
the problem is that if you imagine some arbitrary distribution in the low-rank space of convolution kernels, in general it will not reflect the kernels which we observe in practice. Because we can imagine different low-rank kernels which will not be similar to the ones we obtained during learning. And when we train variational autoencoder, we may more or less guarantee that it will generate us approximately the same kernels like the ones which you have obtained when trained on the large data sets.
So basically you're doing kind of PCA in the space of kernels.
But non-linear PCA.
Non-linear, autoencoder.
Variational.
Yep. So, also we compare different initialization in terms of conversion speed. So here we train both the convolution part and fully connected part, but we like initialize our convolution part with random Xavier initialization, DVP, and filters. Here you can see that when we initialize like wisely, we converge much faster to the same level of accuracy than just random initialization. So that's it. I wanted to point it out that in our work we first propose an expressive prior distribution which is able to encode the intrinsic structure of parameters of convolutional neural network. And second, we developed the method for variational inference with such an implicit prior distribution. Yep. Thank you.
Another question is, which kind of arcane wisdom you used to anneal Kyle divergence term when training networks?
For this experiment, we didn't anneal a divergence. To use
at all, at any.
You know about CFR?
okay, we use some confusion.
Have you used it constant at all time? So better via like approach. Better via like approach when you don't change it during time.
Yeah.
And have you observed some differences?
For all methods, for all priors here.
Okay, have you observed differences in performance when changing beta?
Yeah, it performed better with this. Like
No. The question was if we change beta, will the results change or not for all these three types of priors?
yeah, if we like increase beta, we all these methods will perform worse.
And does beta, have you tried to investigate whether beta is responsible for generalization? Because it seems like when you're forcing, when you're putting more weight on KL divergence term, you enforce more conservative behavior.
Okay, so when you train with any beta here, you can achieve like the maximum like the maximum possible like data term, the good data term on trained data for any beta here. But the high value of beta leads you to like bad performance in comparison to lower beta.
Okay.
I mean, like for any beta you can train your training data set well, but for test data set
So that means that some beta, isn't that big beta results in good test accuracy?
no.
Well, good training accuracy, but bad test accuracy?
Yeah.
That's a bit strange.
Yeah, this is weird.
But
Really
it's
weird.
how it works. For any beta you can like train your training data well, but it's like regularized very strong.
So when you have small beta, you actually make your model more flexible. So
yeah.
it should be more capable of overfitting.
But like the results.
How did you measure accuracy? How did you measure accuracy? You end up with a variational posterior distribution, right? Over the weights. So did you use just one sample or did you use MAP?
No, I used ensemble here. Here and here.
Ensemble.
Yeah, sure. Actually, I like measure the deterministics.
I think when you use MAP solution, this results can consider beta can change dramatically, because
no, actually the deterministic procedure here gives you approximately the same numbers.
You mean the same behavior with respect to beta? Because accuracy, right? Actually, if we set beta say to 1, our model becomes more and more conservative. Conservative models cannot experience the gap between training performance and testing performance, because we limit the ability to feed the training data. The larger beta we have, the more similar is our posterior distribution to our prior distribution. So it may work poorly on test data, but then it should work poorly on training data as well.
Yeah, I see. I mean, when you're training, for example, with standard normal distribution, you like initialize your we use your variational approximation is like Gaussian, yeah, with some mean and variance. And first you initialize your variance with some low value,
right,
like approximately 0, and then it like became gross, and you either can like optimize your alpha so that your data term will be very bad. Okay, you will not train training data at all.
Okay.
But your alpha will be good. But your k-errors will be approximately 0, and your your variance will be 1, and and you don't want such models. Yep. And that's because we didn't actually optimize elbow well, because otherwise we will end up with a crazy model. And that's because if you will optimize elbow good enough, your model will be useless.
You mean that
for small data sets? Yeah, you will optimize calendar runs, which is big. Very big numbers. This scale is very big.
Yes, but this is exactly what Arthur is talking about. In this case, we'll observe poor training accuracy and test accuracy
Yeah.
in both cases. Because the model is too conservative.
Yeah.
We fit too much the prior distribution rather than data term. But you're telling exactly the opposite.
I just forgot about the things that I just explained.
And actually, long time ago, I did some experiments very similar to, in essence, when you have variational encoder, you fix decoder part, and you retrain encoder on some different domain by dropping KL term when you're retraining encoder. You can fit any domain almost perfectly with fixed encoder, with fixed decoder. So if you don't constrain your code space onto the subset of samples that your decoder have seen during training, you can overfit almost on anything. And this is very strange that your results can contradict this.
In what part
Yes.
are they contradicting?
That when you increase when you increase beta, you actually improve generalization. When you increase beta, you decrease generalization. It's very strange because
I just explained this. Like when you increase beta, like set beta equal to 1, yeah. If you optimize elbow, like if you will achieve like the best value elbow as possible, it will get you like KL equal to 0, and then the term is very poor.
yes.
But here in this experiment, to end up with some reasonable models, we didn't optimize elbow as good as we can.
With much better?
No. No, I think with with large beta we here we didn't use large beta.
Okay, we understood it. Here you didn't. But you've told that with large beta you observe the same phenomenon, that you have good data term, I mean training data term, but you have very bad test performance. So probably there's something wrong here.
Yeah.
So we just wanted to know what is wrong. So you perform early stopping with the large betas, or with the large betas you observe that your training error is also quite large?
Here large beta works well, yeah, and we use large beta here.
You mean beta equal to 1? Just like
here we use small beta.
Right.
And that's why we have these like good results.
But the question is what will happen with the large beta?
With large beta equal to 1, for example, if we so we can achieve these results at some stage of our training.
But when you perform early stopping, for example?
Yes.
Without...
And then if we will optimize our like to the maximum.
Okay.
We will achieve 0 KL term and like poor but okay in terms of elbow data term.
So now it seems more or less clear.
Can you please repeat the part with early stepping?
You see when you we used beta equal to 1.
Yeah.
And then if we train with this mini batching over epoch, we optimize our elbow.
Yeah.
And if we stop somewhere at epoch 100, we will end up with good model, something like that. And if we continue training, optimizing our elbow, we will minimize. We will minimize our KL diversions, KL term, almost to 0. But our data term will be poor, and it will perform as random classification.
That's also strange behavior because in all experiments that I ran, if you have too large beta, you from the beginning KL divergence drops to 0. So it's very strange that initially your data term is able to learn something, but
it depends actually on utilization of your variance for Q. for Q distribution. If your variance are very, very low, like approximately zero, like
then the gradient of KL divergence is huge, and it almost like it's first of all it crazes out, and then it goes to 0 KL.
oh yeah, I think we should like write the gradient, and I can take. But what I saw like that it doesn't it didn't the KL divergence at the start didn't optimize as well as you say.
So probably the variances start growing, but very slowly at the beginning. And so you first manage to optimize means, and at this stage you observe low training error. But then the variances start increasing, and your variational approximation converges to prior.
Yeah. Low training and test error.
I think this is possible, and this could depend on parameterization of our variance. So if you optimize in different scales, you could observe for both cases.
What kind of parameterization do you use? Log sigma?
Yeah. It's actually like a big problem with variational inference that if you train your elbow at the best value, you end up with useless model. But still, you can with this model you can like achieve some good accuracy, but your elbow.
There is actually a great information theoretic explanation of these results from Alexander Alemy and company. Well, they propose methods for dealing with this situation by improving actually prior.
So by performing some kind of empirical base?
No, by using, for example, vamp prior to increase. So basically, what you're trying to do is match your marginal posterior with a prior, and by making your prior more flexible, for example, making it a mixture of your posterior approximators, you can you can improve your elbow by not making your code completely useless.
But this is exactly empirical based procedure.
Prior is empirical base.
Oh yeah, actually.
But here we don't have problem with optimizing elbow. We can achieve good elbow.
Good elbow, but not good results.
Yeah, but not good.
Not good test accuracy.
Yeah.
Our goal is to achieve good test accuracy, not good elbow.
Yeah.
And I think that this is a special case of a quite fundamental problem that in case of variational Bayesian inference, when we have a loss of parameters, then KL term starts dominating the data term. This is an open problem, and I hope that well, in nearest future, someone will invent something how to fix the problem. But currently, well, it's still open, and the only way out is to use beta coefficient with beta less than 1 for the most of real live data sets.
I have a question. So why didn't you use the tighter bounds for KL divergence, like the importance weighted variational inference?
You mean for inference or for training?
No, like when you develop an upper bound for the KL with the marginal posterior that is intractable, you essentially re-derive the elbow. So this is very straightforward to apply any elbow or variational inference technique here. And another choice would be to use importance weighted variational inference, like in the weighted variational autoencoders. That will give you a tighter bound on the KL divergence, and it's interesting to see how tighter bound, what's the effect of replacing the true KL divergence by the bound.
Yeah, it sounds interesting. We didn't try, but there is a question: like, do we need actually like this tighter bound?
I think if you don't observe much improvement if you train your reverse model R, you won't observe a lot of improvement if you make the bound tighter.
But it depends on the type of R. Having just one sample in IYE is equivalent to having sort of restricted proposal, and you really need to vary proposal. It's very hard to do so in the fixed parametric family. Unless you maybe go for normalizing flows.
But like, you meant like how it will how our test takers will depend on that. For example,
yeah, like the whole pipeline.
But we, as I said, we tried like normalized flow, where we have no any this upper bound on K-form, where we can approximate, estimate it unbiasedly, and we didn't find any advantages in terms of acres. And
but are you sure?
Did you estimate the marginal log likelihood for the normalizing flows generative model compared to the VAE one?
Yeah, and normalized flows perform better.
In terms of marginal likelihood of kernels?
Of generative model, yeah, but we didn't see any improvement from reducing this gap in generative models in training count models.
Okay.
Another question is that everybody knows that variational autoencoders with factorized conditional distribution suffer from blurring samples problem. Have you observed this problem here, and do you have any idea what will change if you will use, for example, pixel CNN decoder instead of completely factorized one?
No, we didn't explore, but like you can see that it was pretty, like
I think that it's very challenging to see. Probably it may be the case, but I
you
think
have like these columns like
really
7 by 7 or 5 by 5, and like blurry is like what? Like, I mean,
you can still observe blurring
but
effect.
here we can observe.
It's difficult to judge here. Maybe we do. Maybe we are observing it right now. So I think that a good idea is really to try using pixel RNN decoder.
Yeah.
Yeah, and I guess then it will just the posterior collapse would happen.
But again, we can use like problem. We can use normalizing flow, but they didn't suffer. They don't suffer from this blurry problem, and they didn't give us any advantage, as I say. Yeah.
In terms of test accuracy.
Yeah, because our goal is not like good samples of kernels, not blurry samples, but like these test vectors.
Mm-hmm.
Yeah.
And is it possible to generalize this model to IWE or a bound? Because I'm not sure.
Absolutely,
use
100%
distribution.
100%, yes. Like there is all we need is to just lower bound the minus cross entropy. This is what we always do in variational autoencoders. We are having the log density of our model expected over the data generating process, and here the data generating process is our approximate posterior Q, and the infractable density is our marginal prior.
Yeah.
So actually we can use like any bound from VA, since we have this log P.
Okay. Yeah. Good.
Any question?
Another question is, what about distillation of stochastic gradient, longevity dynamics, and stuff like that? Have you thought about it?
Next question will be about relations to the great Fermat theorem. Whether we have thought about
I mean, let's discuss it after.
Okay, if the questions are over, let us thank the speaker again.